In this video here, we're going to take a look at modeling with volumes of revolution. Now we can use volumes of revolution to model real life situations such as the following here. So for example then, the volume of a vase, or if you're a little bit posher than me, a vase, the volume of a rugby ball, and then finally here, the volume of a ball. Now these three examples here are merely a snapshot of the type of things that you will be modeling with volumes of revolution. Now before you watch this video here, just make sure you've watched the previous 3 videos within this chapter here on volumes of revolution. Obviously, if you're completely new to volumes of revolution, I don't think it really makes sense to start here then with modeling with volumes of revolution. So just go back and check the previous 3 videos then, just in case you're completely new to volumes of revolution. So there we have it. We don't really need too much more here then for our introduction to modeling with volumes of revolution. There isn't really anything new here then in terms of the theory. So I think the best way to demonstrate this here then is to take a look at one example. So let's get started then on this example here for modeling with volumes of revolution. So what do we have for this question here? Well, we have a mixed symbol which has a height of 8 centimeters. The shape of the ball is modeled by rotating the curve with this given equation here. So let's just highlight this here then. Through 2 pi radians about the y-axis. So again, this is quite important here. Let's just highlight this as well. So the question then asks us to find the exact maximum volume of liquid that can be contained within the mixing bowl. So to get us started then, all I'm going to do here is just denote this given equation here for y. So y is equal to 0.04 x squared here. So 0.04 x squared, like so. Now we're going about the y-axis here, right? So the result that we need then is v, the volume here, is equal to pi times the integral then. So times the integral here. Now for the limits then, well, the upper limit must be the height of the ball, which is 8 centimeters in this case. So my upper limit is 8. We get 8 there for the upper limit. And then in that case, my lower limit must just simply be 0. Okay, so we go from 0 to 8 here. And because we're going about the y-axis, we now integrate x squared here with respect to y. So I've got x squared then, dy, like so. So clearly then to evaluate the volume of revolution here, we need x squared. So we go back to the original equation here, and we rearrange this and make x squared the subject. So nice and straightforward here then. X squared is simply equal to y divided by 0.04 here. So y over 0.04, like so. But don't forget, if we divide by 0.04, that's just the same as timesing through by 25. So what I get here then is 25y. So I get 25y there. Okay. So in that case then for v here, we can now write this as v is equal to pi times the integral then. So we go from 0 to 8 again. Just notice the limits don't change. So from 0 to 8 here of x squared then, which is 25y here. We get 25y there with respect to y here, so dy. Okay. Now this integral here then, to evaluate this, nice and straightforward, just basic A-level maths integration. So what do I get here then? Well, I get pi times by, we add 1 to the power, divide by the new power. So I get 25y squared. So 25y squared all over 2 here. Okay. And again, don't forget the limits here. We go from 0 to 8 here. So from 0 to 8 then, like so. And then to finish with here then, all we need to do now is substitute our limits in here. So again, we start with the upper limit and then we subtract the lower limit here. So again, just basic A-level maths integration. I get pi here times by them. So I get 25 times by 8 squared over 2. So 25 times by 8 squared, well, that would be 64. And then we divide by 2 here, like so. And then we subtract the lower limit here. So we do minus 25 times by 0 all over 2. Obviously, this second part here will just be 0 anyway, but I'll just write it down just for clarity. So in that case, then what do I get here for v? Well, in that case, then, this part here will just be, well, 25 times 64, divided by 2, we get 800. So I've got pi times by 800, which would give us 800 pi here. Okay, so we get 800 pi there. And there we have it. So The exact maximum volume of liquid that can be contained within the mixing bowl is 800 pi, and don't forget the units here. We're working in centimeters, so our units then are centimeters cubed here. Okay, and there we have it. So that gives us the solution there to this example, and that brings us to the end then of this video here on modeling with volumes of revolution.